Hello everybody. Till now we had been studying about one very specific two-port device, and that was the transformer. Transformer, as you understand, we discussed it quite early, was one of the two-port devices that we were supposed to discuss, and it takes the electrical energy from one side called the primary and delivers the electrical energy on another port called the secondary, and that is also the electrical energy. And we modeled the transformer, studied its equivalent circuit, and got to know how it operates, the principles of the transformers, and the various non-idealities which go up to make a practical transformer. Today we shall begin our discussion of another two-port device, which is the DC machine. The DC machine is also a two-port device like a transformer. However, it has one fundamental difference, and that is the voltage or the effort on one side is related to the flow or the through variable of the other port. Likewise, the flow on the electrical side is related to the across variable or the potential variable or the effort variable on the port 2 side. And another point to be noted is that in a DC machine, one port is electrical in nature, meaning the quantities that are going to be applied to one port is electrical quantities, and the quantities that are applied in the other port are the mechanical quantities, because it is in the mechanical domain, mechanical rotational domain. So, torque and omega will be the effort and flow variables, that is the potential and the through variables, potential and the kinetic variables, and in the case of the electrical domain it will be voltage and the current as usual. So, we are going to discuss another two-port device called the DC machine. There is going to be energy which gets energy which flows into the machine through one port, and we will call that was port 1, and energy flows out through another port, and that is called port 2. One port is electrical in nature, meaning port 1, let us say, is electrical domain. Port 2 is in the mechanical domain, mechanical rotational domain. This means the potential variable and the kinetic variable on the electrical side is the voltage E and the current I in amps, volts and amps. Product is going to be the watts, and the potential variable on this side is torque in Newton meter and omega in radians per second. So, this is volts, this is amps, this is torque in Newton meter, and this is radian per second. So, E E on one side, torque on the other side are the effort variables or potential variables. I on the electrical side, omega on the mechanical side are the flow or the kinetic variables. The product of effort to flow on each side is always going to be watts, that is the power flow. Now, if the energy is flowing in this direction as shown, which means from the electrical to the mechanical side, then the same device is called a motor. If the energy is flowing from port 1 to port 2, that is the electrical energy is converted into mechanical energy and used for driving something, then the DC machine is called the motor. The same instrument or the equipment can be used in a way wherein the energy flows from the mechanical to the electrical, meaning something rotates the mechanical shaft of the machine, and that is going to induce the electrical side parameters, and therefore the energy from the mechanical side can flow, that is the energy from the mechanical side can flow to the electrical side, and under such conditions the device is called a generator. As the effort on the flows on the electrical side are DC values, the motor and the generator, both in the case of motor and the generator, the machine is called a DC machine. So, this is the machine that we are going to focus now and try to understand its principle of operation, the basics, the concepts, what makes it happen, what makes it rotate, what makes it generate. So, first we consider the DC machine as a generator. So, we discuss the DC generator, and the same machine will be later discussed as a motor, that is it transfers energy from the electrical to the mechanical domain. Most of the principles that we study when about the DC machine as a generator will also be applicable to the same machine which will be in the motoring mode. So, these two functions of the DC machine we will try to focus on this class and the coming classes. But before that, we need to know one or two small principles, like we had the Faraday's laws of electromagnetic magnetism in the case of the transformers, which form the basis. Here also, of course, we will be using Faraday's laws of electromagnetism, because the energy is passing now through three domains. So, you see that the energy, let us say if it is in the case of the generator, ultimately you will need to have the energy in the electrical domain. The energy emanates from the mechanical domain as far as this equipment is concerned, and it passes to the electrical domain through an intermediary medium, and that is the magnetic domain. So, energy passes from the mechanical domain into the magnetic domain, and from the magnetic domain to the electrical domain. So, therefore, three domains are involved. And in the case of motor, the energy emanates from the electrical domain and goes into the magnetic domain, and then from the magnetic domain it goes into the mechanical domain and causes the mechanical movement. That would be, the green arrows indicate the motoring direction for the energy flow. You see that electrical domain to the magnetic domain to electrical domain, the principles here are very similar to that of a transformer. All the transformer principles, the Faraday's laws of electromagnetics, all those things are valid. There are few rules that we need to know for mechanical to magnetic domain, and that is, one is of course the Faraday's law, and another is the Lorentz force. Lorentz force. These two laws are applicable in this transformation of this domain. Now, let us take a piece of magnet and let us call it as north pole, and somewhere there on the left side you will see the south pole for that piece of magnet. Let us take another piece of magnet, and let me give it some space. Let us take another piece of magnet and place it at some distance in line with the north pole, but the south pole facing the north pole, and this has a north pole also, of course, because no magnetic element can be with an isolated pole. So, it has its own north and south poles, but we are interested in this, that is up to here. Now, here if you see the magnetic lines of force, this is at quite some distance, it is not quite near it, because this is much further than the distances that we are indicating here. So, that this north pole does not have much interaction with the field lines which are occurring here. Okay. Now, if we take the field lines, there is a flux from the north to the south. It starts going from north to the south. It is quite strong north to south, but in this direction, the field in an orthogonal direction is 0. Now, in an arbitrary direction at an angle, the field is going to exist, but it is going to keep decreasing. Let us say we take the we draw a circle. Let me draw a circle. As shown like that. So, we have a circle here, and if one travels along the periphery of the circle, at this point the field is strong and positive. At a point here, the field this is at a point which is orthogonal to this north south axis, and the field there is 0 in that direction. At any other direction, let us say at when we are at a point here, then the field will be a bit reduced, would be a bit reduced compared to the position on this, because it is not directly in line. And then if we take a point somewhere here, the field will still further be reduced, and still further if we take a point somewhere here, the field is positive still, but still further reduced, and so on till it becomes 0 at this point. And then further, if I consider a point on the circumference here, in that direction the field starts becoming negative, because if we consider a point here, with respect to that point, the field is going to the point, not away from the point, and therefore, at corresponding to this point, the field direction is negative, and it is shown by this negative arrow. And as this point starts in this circumference, as this point starts traveling like this would be going in this fashion with increasing field gradually till it becomes maximum and negative at this point. So, you see that there is the field goes in this fashion, in a sinusoidal fashion here. Now, with a maximum when it is at the north pole, negative maximum when the position is when a point is at the south pole, 0 at both the orthogonal points. So, when the point starts moving at this point, we see again the mirror image of this, and then when this starts moving again towards the orthogonal axis, you will see the field decreasing. Field starts decreasing until it is 0 at the orthogonal axis, and as the point further continues, it becomes positive, that is, this is the positive direction, this is 0, this is the positive direction. So, field again changes direction, and you will see that radially there is different amplitudes till it reaches the positive maximum when the point has again reached this point. So, you see that if there is a point which is situated on the circumference of the circle, starting from the north pole, the point located near the north pole, if the field is moving away from the point, we are putting it on the right side of this axis, and the field is on the south pole, the field is entering the point, and then that is considered as negative. So, a point which moves around the circumference like that starts with a field which is positive and then keeps decreasing as the point is moving along the axis there, decreasing in this sense till it becomes 0, and then it goes negative in this portion of the segment, keeps going so on till the field is negative maximum, till it is negative maximum as shown here at the nearest to the south pole point. And as the point traverses along the circumference towards again the orthogonal axis, this traverses, the amplitude starts reducing further again till it becomes 0 when it is at the, when the point is at the orthogonal point, and then this goes again in this direction, changes direction and becomes positive max when the field again goes to this point. So, this is how the field would look like when a point traverses on the circumference as shown here when we place north and south poles. So, this would be the 0 of the field phasor, the field vectors. Okay. So, this would be the picture of the field vector. Field vector spatial picture. Okay. Now, let us have a north pole and a south pole, and let me have a conductor with some as such there is no such current in the conductor. Let us say that there is a field which is existing from north to south in this direction. Now, this is a conductor. Now, this conductor, if it is stationary, the field that is linking the conductor is also constant. There is no d phi by dt. So, as there is no d phi by dt, there is no induced voltage in the conductor, and therefore, there is no current flow in the conductor. If the field is changing, if the amplitude of the flux here, amplitude of the flux phi here is changing, then there is a d phi by dt, and this results in an induced EMF in the conductor, which will result in a current to flow through the conductor in a specific direction. So, therefore, what is essential is a changing field for a current, for a voltage to be induced in the conductor and thereby a current to flow in the conductor. Now, there are two ways in which to produce a changing field as far as the conductor is concerned. Let us say the conductor is fixed at a point. Now, the flux phi here can change with respect to time. Flux is a function of time. Then amplitude here changes, and therefore, d phi by dt is finite, not 0, which will induce a voltage across the conductor and thereby a current to flow. The other way is to have flux fixed. Flux is fixed, the flux amplitude is fixed. You have a permanent magnets north and south pole, and therefore, the distance between them is also fixed, and therefore, the flux phi is fixed. Under such condition, the only way that you can have a change in flux is if the conductor moves. If the conductor moves, let us say to this position, then the flux at that position, which is at a radial angle, is going to be lesser, and if it moves still further, the flux is going to be lesser. If it is at the orthogonal axis, the flux there is going to be 0, and let us say it continues to move. So, the flux amplitude that is going to cut the conductor is going to keep changing as the conductor moves along the circle. So, that is the movement of the conductor is going to give you the d phi by dt, which is going to induce the voltage and thereby a current to flow. So, this is the other method in which induced EMF can also be produced in the conductor. So, in the case of DC machines, the flux here is kept constant by means of the fixed permanent magnets, let us say, or something that produce constant flux, and thereby the only way that you can produce an induced EMF in this conductor is by moving the conductor along the periphery, which means that this conductor is going to see varying amplitudes of the flux at different amplitudes at different points on the circumference of the circle, and therefore a d phi by dt, and therefore a induced EMF, and therefore a current to flow through the conductor. This comes by from the Faraday's laws of electromagnetism, where you know that the induced EMF which is equal to n d phi by dt. An alternative expression in terms of the conductor length can also be derived, which is, let us just modify the okay, and then we have this. Okay, so these are the magnets, and then of course there is the conductor. Okay, so this conductor is positioned like this, and then you have all the flux lines linking the north and the south poles. Now, if this conductor is having a length L, and then there is a cross section area AC, and therefore flux by AC is going to be the magnetic flux density B, and then if the conductor is moving at some speed, let us say V is the velocity in meters per second at which the conductor is moving, cutting across the flux, then the voltage induced is also given by B, the flux density, which is a constant of course in this case, because phi is a constant, AC is a constant, L is a constant again because this is the length of the conductor, and V, which is the velocity at which this conductor is moving in meters per second, and this is what is cutting the flux, and therefore as it is moving, it is at various radial distances, angular distances from the center, and thereby the flux amplitudes are going to be varying at different positions, and that is going to cause the d phi by dt effect, the d phi by dt effect here, the meters per second, and it is going to result in a induced EMF in the conductor. So, the induced EMF in the conductor, this gives the induced EMF in the coil, which has N turns. This gives the induced EMF in the conductor, which has length L, moving at speed V meters per second. So, both are actually one and the same law, Faraday law of electromagnetism. Whereas one is with reference to the coil, the other is with reference to the conductor. So now we start again with the north pole here, and we have a south pole here, and let me also have a circular marking which gives the periphery in which the conductor is going to rotate, is going to move about. So, let us now have a conductor which is positioned like this. So, once we have the conductor, this single conductor positioned like that. Now, let us see the current through the conductor as it is moving along this field here. So, as it moves, let us also take the position, consider an imaginary, now let me draw with a different color, consider an imaginary xy axis . This is spatial, this is a spatial axis, spatial coordinate system. So, when the conductor is in this position, the flux is full max, and the conductor starts rotating from here to this point, moves from here to this point. The flux at these points are gradually decreasing until it becomes 0 here. So, you have the flux which reduces becomes 0 at this point. Then from here to here, the conductor is at the south pole, the flux is at negative max, and then when it further goes, the flux keeps moving in this fashion, 0 again at this point, and then when it again moves here, the flux value is back again to its positive max. This is the 0 as far as the flux phi m is concerned. So, this is the alpha axis and the beta axis in the spatial coordinate system. Now, when the flux is at this point, we are talking of this maximum. So, therefore, you have the induced EMF E which is equal to B L V. The B is maximum at this point, the induced EMF is maximum, and therefore, the current which is going to flow through the external load is also going to be maximum. So, if we now project this on the temporal axis, let me now draw the amplitude of E, the induced EMF, with respect to time. So, as it is at this point, let us call this as A. So, this point is A that we are going to begin. Okay, this is at 0, sorry, this is at peak. Let me so it is at this point, this is 0. So, this is at E max then it rotates 90 degrees and it becomes 0 here, and then from this is point B, this is point A, this is point B corresponding to the spatial, this point C and D. So, from B to C, this is going negative. So, this starts going negative and reaches the maximum point C in the other direction, negative direction, that is here, and then from C to D it again becomes 0 in the orthogonal axis orthogonal to the alpha axis, which is along the north south pole direction, and then from there this is point D, and then again D to A. This again is point A, comes back to. So, this keeps going on and on. This is for one complete cycle of rotation. You see that you get a almost sinusoidal voltage that gets induced on the conductor as the conductor is moved from A to B, B to C, C to D, and so on. Now, this gives the basis for generating some voltage from the mechanical rotation of a conductor to an electrical induced voltage. So, let us now form a device like this. Now, let us have the north pole like that. So, this is our north pole, this is our north pole, and let us have our south pole, so this is our south pole. So, you have flux lines from north to the south. Now, let us draw a coil right through here. So, we have a conductor of length L, there is a conductor which is this, there is also another conductor which flows through like that. So, this completes the circuit. So, let us have some mechanism whereby I will have a ring. I will have a ring here. So, let me have the ring in a different color. So, let us say I have a ring like this, and let us solder this wire onto that. Okay, it is soldered. Likewise, let me also have a ring for the other wire also. And let me solder and this to this. We have this wire which is made in the shape of this coil here. The two ends are soldered to two rings, and let us call this one as ring A and ring B. And to these rings, let us add we have two carbon brushes like this, which are just touching these rings. We have two carbon rings, and these carbon brushes are making only spring contact with that one, and through this we bring out the leads, and then we can now connect a load resistance. This is the load. We have a very simple we have a very simple generator, not a DC, general generator, which generates AC signal. Okay, let us look at the operation of this one. Let us say that this coil is moving, rotating. So, by some mechanism we are going to provide energy, mechanical energy, such that this whole coil is made to rotate about a axis. So, this whole coil is rotating about this axis, that is let us have this axis. So, the whole coil is rotating along the axis, the blue line as shown here. Now, this conductor here, when it is at the north pole, this is going to have a positive field, as we saw before, positive max field, and let us say the current is going to be induced in this direction I. There is a current I which is going to be induced in this direction, and this conductor is closest to the south pole, and this is going to have negative max field, and there is going to be a negative current of other direction, same amplitude, going to be induced in this. Now, this is in a perpendicular direction, this is along the field. This portion of the conductor does not cut the field, does not see any differential flux amplitudes throughout its rotation, and therefore, there is not going to be any induced EMF on this line, there is not going to be any induced EMF on this line and this line. So, these two are going to have currents which are going to get induced, one in this direction, one in that direction, and this is fortunate for us because we have drawn the coil such that current can flow like that through this coil, flows through this coil and comes out through this. So, as the slip rings, that is, these are called the slip ring, these rings which are soldered to the coil ends along with the coil are rotating, it is brushing or making contact with these brushes which are fixed, of course. So, it is rubbing against these brushes, which means it is in constant contact with the brush. So, a current this current which flows through here like this comes into contact through this brush, flows through this external load, and then flows in this direction, and then again flows into the other coil A through this ring and the soldered coil end, which completes the circuit, and thereby you get a output here, induced output here. So, as the whole coil is rotated, we see that the voltage across the load, E load, which is the induced EMF across the brushes, starts with, now in this position it will be having a maximum north and south, because the north and south are going to produce these aiding currents, and as it starts rotating and takes an orthogonal plane, this is going to pass through 0, because when the coil is perpendicular in a plane which is perpendicular to the plane which is right now shown, it will be 0, because there is no flux in the perpendicular plane. And then when it starts again rotating towards further towards the south pole, that is this portion rotating towards the south pole, it starts going in the other direction, and then again when it becomes perpendicular to the existing direction, orthogonal direction, there is no flux, and then so on, it keeps going like this. So, when the flux is in this position, the position which is like this, let me remove all these things, let it be easier for you to. Now, I will show it in a different color. Let us say the coil has now taken the position which is like that. And this has gone like that. That is, it is this vertical position. Probably it is confusing. Let me redraw that one. It is better to look at it like this. Let me make some space here. Let us draw the 4 possible modes in 2D, so that you get a good idea. This is north, this is south, north pole, south pole, the north pole, south pole, the north pole and the south pole. Now, we are going to show the conductors in 2D as just the cross section. When you cut the section of the coil, and it is going to be in this position, and then rotates again and comes into this position, and rotates and then comes into this position. So, let me call this one as coil side A1, A2, A1, A2, A2, A1, A1, A2. Okay. So, if you look back to the previous figure, this is A1, this is A2, and the current going into the page, we are going to put the X mark like that, and coming out of the page is like this. So, as the coil has rotated, as the coil has rotated 90 degrees, you will see that there is no current flowing in this position, because the induced EMF is 0. And the coil further rotates in the other direction, which makes this is in this direction. However, the direction in A1 and A2 have interchanged. You see that the direction has changed in A2 and so in A1, and therefore, we are showing it as the negative direction here, this portion shown as the negative direction. And when it comes again to this point, it again becomes 0, no current flow in any of the coil sides, and then from here it shifts here. So, this is position 1, position 2, position 3, position 4, and then back again to position 1, 2, 3, 4, so on. It keeps flowing in this fashion. So, this is the various positions, the four important positions in the motor in this particular equipment. So, what we have here is a generator, but it generates an AC waveform. How do we generate a DC waveform from this? Means, how do we rectify it? So, if we pass it through a rectifier, we get from the AC waveform that the AC induced voltage a DC. But we are not going to build the rectifier using diodes, but it will be built in along with the motor here. So, let us make a slight modification in the way the motor is built. Let us have again the north pole and the south pole, and let us have a coil here. Now, this coil is shown like this. In this fashion. See, the poles can of course be extended. And we have the north and the south pole like this. Now, this coil is now connected to the rings in this fashion. So, let us have a ring in this fashion. Now, this portion, this one end of the coil is now soldered to this. Probably we will solder it from the inside, so that the brushes. So, we solder one end of the coil to this, and the other end of the coil is soldered to in this fashion, let us say. there is a vertical split in the ring such that this portion of the ring does not make contact with this portion of the ring. And then we still have the brushes. We still have the brushes like that, which is making contact. We still have the brushes which is making contact, and this from the brushes we are going to take it to the external load like this. So now what happens? We have the coil side A1, coil side A2. Now this right now this is going to induce a current in this direction here and in this direction here, flows through the external circuit, and the current flows through this coil. Now as the coil is rotating and comes in an orthogonal plane, it becomes 0, the voltage becomes 0 and starts going negative. So when this has turned 90 degrees, these two splits are going to be at around the center of the brush, and then on further rotation, this split, that is, let us say this is A1 and this is A2 portion of the ring. So the A2 portion of the ring is going to be in contact with this left brush, and A1 portion is going to be in contact with this. But at that point, when it has crossed over the orthogonal plane, there is a reversal in the current for A2 and A1, and therefore A2 becomes positive and A1 becomes negative. So therefore you would see in the time axis, temporal axis, time versus the induced EMF E here. So it starts with a peak like that, and then the moment it comes to 0 here, when it is on the orthogonal plane, flux is 0, and now on further movement flux would actually have gone negative, but here the other ring is now making contact with this brush. The ring which was positive is now making contact with the other brush, and therefore there is a reversal in the contacts with the brush, which is again going to make the current through the load in the same direction, and this is going to go like that, so on in this fashion. So there is a rectification which has come about due to the way in which this ring has been made. This is called the commutator. The way the ring was formed in this case, in the AC motor, this is called the slip ring. So the commutator can be used for obtaining a rectified waveform at the output, and thereby we get a unidirectional induced voltage, and therefore that would be a DC output. And therefore this machine with the commutator, even though the current through the coil is both directions, that is AC, because of the external commutator, the voltage across the external road is unidirectional, the currents through that one is also unidirectional, and therefore this can be considered as a DC generator. We stop here and continue in the next class consolidating the concepts of the DC generator further. Thank you.